happening, and it's great. So I want to tell you things about Whitney numbers of the first and second kind, or maybe the second kind and the first kind, depending of how you want to see it. Most of what I'm going to be talking about is joint work with George Hallam, mostly, and also with previously a student of a master student from Universidad Nacional that we met at one of the events that the Colombian Combinatorics community organizes. This was at the Dias de Combinatoria in 2017. I think some of Laura is going to be a speaker this time, and it's a great conference. We met we were in the different universities. This is Yeison over here. Most of you know Josh, and I think I saw Josh also in the group today. So the usual suspects for me that are always. Are you guys hearing me? Okay. I said yes. I heard some feedback. Okay. So my usual suspects are always posets. I really like to work with posets. This is a picture of a poset that is familiar to some of you. This is the poset of partitions. So it helps me to introduce the notation. So the poset of partitions of a set, in the bottom we have all singletons. Let's say 1 is in its own block, 2 is in its own block, 3 in its own block. And when we go up in the poset, we start merging blocks. So we merge the 1 and 2, and we end up in this element here. And I also want to ask you, like, normal people see the cursor when I am pointing to things? Is this a good idea to use cursor? Okay, good. And then if I merge the block 1, 2, and 3, then I get all the way to the top. So in particular, this partially ordered set of posets has a bottom, and the posets that I'm going to talk about in this talk have a bottom. There is also pure or graded, so it's organized in floors. And when I have a poset like this, I can start playing a game, the Möbius function game. So I'm gonna start in the bottom. Let's say I'm gonna define recursively the Möbius function. So the Möbius function from the bottom to the bottom is just 1. And every time I go up in an interval, then the Möbius function has the values of the Möbius function need to add up to 0. So in particular, these values here in the middle should be -1 all, because these intervals, let's say from bottom to the partition with the one block 1, 2, /3, has to sum up to 0. So this is a -1, and the whole big interval has to have a value of 2. So this is the Möbius values. So again, this is a recursive definition. You start with a 1 in the bottom. Every interval has to add up to 0 if it's a non-trivial interval. So for example, this value in the whole interval should be 2. Taking the Möbius values, and since we have this building formed with floors, we can start adding the numbers, and we get what we call the Whitney numbers of the first kind. So basically, add how many numbers of Möbius value you have in the bottom. You have a 1, in the middle ground you have -3, and in the top you have a 2. So the Whitney numbers of the first kind for this poset are 1, -3, and 2. I want you to keep in mind these numbers, because these numbers are going to show up a little bit more. Also, the Whitney numbers of the first kind are very famous also because they appear in many other disciplines. In particular, they appear as coefficients of the chromatic polynomial. These are the coefficients of the chromatic polynomial of the complete graph. So these are very well studied numbers. These numbers require that you compute this recursion and then add up, but there is a simpler set of Whitney numbers. These are the Whitney numbers of the second kind. Just how many elements do you have at each floor? So in the first floor you have, in the 0 floor you have 1 element. In the first floor you have 3 elements, and in the second floor you have 1. Actually, these are like the floors in Chicago that the third floor actually happens to be the fourth floor. So we start at the 0. So we have the first numbers of the Whitney numbers of the first kind, of the second kind. For the poset of partitions, they are known also as the stealing numbers of the first and second kind. Okay. So this is kind of the object that I want to talk about. But let me show you another example. I'm going to play the same game in another poset. So this poset, we call it the increasing spanning forest poset. So we start now on the bottom. We have a forest. Actually, all of these elements 1, 2, and 3 is a forest of rooted trees. In this particular case, 1 is just a forest with its own root. And to go up in the poset, we are going to start merging roots and choosing the smallest. So if I merge 1 and 2, I choose the smallest, and then I go up to this element here in the left. Okay. So can you give a thumbs up if you are seeing the cursor when I explain? Okay, yeah, because I could be very awkward if you are not seeing what I'm pointing to. Okay, so if I merge these two trees, so I have the root this here is 1 and 3, and I merge the roots, I choose the minimal, I get all the way here to the top. So let's play the same game again. So we compute the Möbius numbers, and then we compute the Whitney numbers of the first and second kind. So the Möbius numbers here now, notice that this element now has a 1, because all of this interval here needs to add up to 0. But now this Möbius number here is a 0. Because if we add all of this interval here we already have a 1, a -1, then this is a 0. Okay? And I computed here the Whitney numbers of the first and second kind, and they're hard to see, but I'm gonna put it in this little table. So here in the left, you will find the Whitney numbers of the first and second kind for the poset of partitions by 3, and the Whitney numbers of the first and second kind of the increasing spanning forest. And I want you to stare a little bit to these numbers. So it's 1, 3, 2. Forget about the minus sign, because this minus sign in these two posets are predictable, are just alternating for the Whitney numbers of the first kind. And so you will start noticing a pattern. In particular, the pattern is that the Whitney numbers of the first kind of the increasing spanning forest end up being the Whitney numbers of the second kind of the poset of partitions, and the second kind end up being the Whitney numbers of the first kind. So this is kind of we saw this as a very, very particular phenomenon. So basically, again, so what I'm trying to point out here is that the Whitney numbers of the first kind and second kind from the poset of partition now here appear the other way around. So we decided to call this phenomenon Whitney duality. So basically, you have these two posets, graded posets and with a 0, to be able to have in this setting that we count Whitney number from the bottom, and also we have floors. We call P and Q Whitney duals if this phenomenon happens. The Whitney numbers of the first kind in absolute value happens to be the second kind of the other one, and the second kind happens to be the first kind. So according to this table, the poset of partition pi 3, and actually in general pi n, is a Whitney dual of the increasing spanning forest. You can prove this directly just by looking at the numbers. These are the Stirling. Remember that these are the Stirling numbers of the first and second kind. It is not very hard to show that the Whitney numbers of the first and second kind in the poset of increasing spanning forest are also switched. So you can prove this directly. But I'm going to show you actually another proof of this. So we started to look at this phenomenon that was very curious for us, and we wondered what other posets have Whitney duals. So the first poset that you will have into consideration is always the Boolean algebra. And the Boolean algebra has this phenomena that basically the Whitney numbers, the Möbius values are either plus or minus 1. And they alternate in sign. So if you just ignore the sign, so every time we are adding the same numbers, either for the Whitney numbers of the first or the second kind, and then we will say that the Boolean algebra is its own Whitney dual, or Whitney self-dual. The Boolean algebra is not alone, so all Eulerian posets have this property. So there is a bunch of Whitney duals, but somehow it's kind of a simple example. So it's more interesting the example in the poset of partition, because I mean the numbers are not all ones. Yeah. So, but there are also, this is not a trivial property. There are other posets that are very common posets, like a chain, that stop having Whitney duals. In particular, if you have a chain with 3 elements, now you start having zeros. And then if this chain had a Whitney dual, then it will have no elements at level 2, but with a Möbius value of 1. So zeros are clearly problematic for this theory. They're not completely problematic, but for what we do, actually, zeros are very problematic. There are other posets less trivial than this that also don't have Whitney dual. So basically, it's not a trivial property. Not every poset that you can construct graded with a bottom is going to have a Whitney dual. So how do we construct Whitney dual? So this is kind of the story that I want to tell you today. So we wanted to use the techniques that. Sorry, is there any questions so far to hear? Yeah.
I just missed something really quick. Can you just really fast again say what the Whitney number of the first kind was?
Yes.
How was it defined in terms of the Möbius? Sorry to go back.
Yeah, no, that's perfect. Thanks, Maria, for the question. I
appreciate there it is. Okay.
So basically, you first compute the Möbius values from the bottom.
Right.
So these are the red numbers here. And since this is a building with floors, we add at every floor what is the number.
So you just add like the -1s across to get the -3. That's what I missed.
The
Thank you.
-1 because yes.
Got it.
Thanks for the question. This is very helpful.
Thank you.
Yeah. And actually, it involves first the recursive definition of the winning of the Möbius numbers, and then to add, but then the winning numbers of the second kind that are simpler. Yeah, you just add them. I mean, simpler in some sense. Yeah, for some other investigations are not that simple, but in this case, you see, if you're counting, it's very enumerative directly question. Okay. So I come back here. So we investigate.
Rafa?
Okay, what? Yes.
I think there's also a question in the chat from Steve.
Thank you.
So he asks if a poset has multiple Whitney duals, is there supposed to be a canonical dual?
Yeah, so actually this is a question that I want to address today. So let's say we received this question a lot, Josh and I. We were talking yesterday about this. So we call it dual because this is how we started thinking about it. And you should think this as a phenomenon of the sequences of numbers. Yeah. So think about it, even the problem of if you have two sequences of numbers of let's say non-negative integers that you want to see if there is a poset that has the winning numbers and the first and second kind of this sequence. This is a hard problem. Yeah. This is a hard problem. And then now this is even the question is like, can even you swap and find a representative P and Q that one has the winning numbers of the first and second kind and the other second and first kind? This is more or less that we are attacking. So the Whitney duality is more about the sequence of numbers. It's not about the poset. So yeah, so there is a non-uniqueness component of this. That is part of my punchline at the end. So we'll talk about this. Yes. Thank you, Steve.
I suppose one can think of them as equivalence classes. Like you have an equivalence class of posets according to like its Whitney numbers. Right? And
you would like, so in principle, you would like to see what these elements in the equivalent class have in common. In this moment, they only have in common the Whitney numbers of the first and second kind. Yeah.
Right.
But they might have more properties. That this is actually an interesting direction to study. So the two ingredients that we want to use are the edge labeling and quotient posets. So in particular, an edge labeling. Some of you are aware of edge labelings. So we take the edges of the Hasse diagram, like we take this as a graph, the poset this picture as a graph, and we take another poset where we are going to put some labels. And this is the poset of labels here. Sorry. So we have another poset that has labels, and we label the edges. So this is an edge labeling. And in particular, we could see some property that these chains, the saturated chains, even from the bottom of saturated chains can have. Some of these chains are increasing. So for example, here the chain 1, 2, 1, 3 is an increasing chain. Some other chains are not increasing, like 1, 3 and 1, 2. So we have these two type of chains, the increasing, the asymptotic or the non-increasing. There are other chains that sometimes increase and sometimes not, the non-increase and so on. And notice that I'm saying non-increasing because the deposit of labels could be a partial order. It doesn't have to be a total order. In particular, I'm going to concentrate in the increasing and the asymptotic chains. So if in every interval I have a unique increasing chain, we are going to call this labeling an ER labeling. And if in every interval we have a unique, never increasing chain, we are going to call this a dual ER labeling or ER star labeling. So these are two types of labelings. How they relate with the Whitney numbers. So sorry, here in this picture, I have two examples of an ER labeling in the left and an ER star labeling. So if you look at the poset in the right, this every interval, in particular, these two non-trivial intervals in the right and in the left, you see that they have a unique not increasing chain. So we have ER labelings and ER star. And Stanley related these type of labelings with the computation of the Möbius values. In particular, if you have an ER labeling, the way to compute the Möbius value is to count asymptotic chains. And the same proof of this theorem works to say, like, what happens if you have an ER star labeling? Oh, then the Möbius values are going to be the increasing chains. Okay, so there is certain duality between increasing and asymptotic chains. If you have an ER labeling, the Möbius values are the asymptotic chains. And if you have an ER star labeling, the Möbius values are given by the increasing chain. In terms of the Whitney numbers, we can rephrase this theorem like this. If you have an ER labeling, the Whitney numbers of the first kind are counted by saturated asymmetry chains from the bottom, but the Whitney numbers of the second kind are counted by increasing chains because the increasing chain is unique, so every element is actually recorded by its increasing chain. If you have an ER star label in the rows chain, now the Whitney numbers of the first kind is counted by increasing chains, and the Whitney numbers of the second kind are enumerated by asymmetry chains. Okay. So we created a new type of labeling that we call an EW labeling. So an EW labeling has the following property. It's an ER labeling. Also has something that I'm going to describe that is called the rank to switching property, and some other injectivity condition. The injectivity condition I'm not going to discuss it here. It is necessary for the proof. We believe it's necessary for the proof also of the theorem that I'm going to say, but also in most of the labelings that we have found is kind of natural to have it. It doesn't have to have it, but it's natural to have it. But the rank to switching property is actually very key for the proof. So the rank to switching property is every time I look at the rank to interval of my poset, we know that there is a unique increasing chain because it's an ER labeling. That this unique increasing, let's say AB comes with a friend, with BA. So you have another chain that is unique and you can reverse an increasing step. You cannot like order it to a decreasing step. So this is the property that we want. So an EW labeling, or sometimes we call it Whitney labeling, but let's say EW labeling, is an ER that also has the rank to switching property. And something that I'm putting behind the rug, that this injectivity condition, that is also necessary. Okay, so the main theorem that we have is if we have a poset, like the ones that I have shown you, with an EW labeling, then it has a Whitney dual. So this is the main theorem. And not only has a Whitney dual, but it's not like it's a constructive proof. So we can tell you exactly what is the Whitney dual we are talking about. Okay. So this is kind of the main theorem that we have so far in this theory of Whitney duality. So how is the construction? So let me just show you why this. I mean, it's a little bit, the general case is a little bit more complicated than this, but in this case, it's very good to illustrate. We start with our poset, and we construct another poset that we call the chain poset. They saturate chains from the bottom. So in the bottom, you have only the element, the zero element, and then let's say you have the bottom with 1, 2/3. This is this saturated chain, and this is included in a longer chain. So it's almost like you take the poset and you spread it out like a tree. And then we have this rank to switching property that allow us to do quadratic exchanges. So we're gonna be doing quadratic exchanges. Every time we see a rank to switch that we do it. So we take this poset. These are actually the words of labels in the poset in the right. And every time we can make a switch. So we can make a switch between this chain in the left and this chain in the middle. We are gonna make. So I can make a switch here, and I'm gonna identify these two elements, and I take the quotient. So you see, this poset looks very similar to the poset of increasing spanning forest that I showed you before. We can even take this labeling from the first poset and kind of put it in the second poset. It is crucial for the proof to show that this is actually an ER star labeling. And so just this is actually a poset that we obtain. So in this case, if you see, for example, here, the edges 1 and 2, 1 and 3, what is actually the edges of these 3 so far. So actually, this theorem is proving that these two, you can prove it directly. You don't need the theorem, but this theorem with this ER labeling proves that these two families are Whitney duals. Okay, so this is the kind of the construction. So now let me tell you a little bit about, so this is kind of the main theorem. So every time, so this thing that looks complicated from the very beginning, what kind of sequences, pairs of sequences will have two pairs of posets, a pair of posets that are Whitney duals to each other. We can attack this with Whitney labelings, and a lot of the ER labelings that we have found in the literature have this property. So we are just studying some of them. So let me show you some examples. So the first one, and kind of big example for us, is the word of geometric lattices. I think there must be some questions in the. Sorry, am I missing some questions in the chat? Oh yeah,
I think Josh was fielding them.
Josh is helping me to answer. Okay, thank you, Josh. So the big example is geometric lattices. So there is this minimal labeling of geometric lattices that's standardly defined. So every time you have an edge, like a coed relation, you take the minimal, you order the atom in a linear order, all the atoms in a linear order, and you take the minimal atom that takes you up. This is, people know this as the minimal labeling. And we prove actually that the minimal labelings are all EW labelings. Basically, the moral of this is all geometric lattices are Whitney dualizing, even in multiple ways, to answer the question of Steven before. So you take one of these minimal labelings, you construct the Whitney dual, and now you have another poset. Normally, these posets come with a lot of combinatorial structure. Think about, for example, MVC sets. Yeah, the other poset will be a poset in MVC sets. And then, but the Whitney numbers of the first kind that were kind of more complicated become the second kind that were kind of easier, and so and the other way around too. So all the work of geometric lattices is here, and this is kind of one of the big selling points. Let's see. Yeah. Thank you, Josh. And the other example that I want to show you is come from an operatic theory. So actually, we have more examples. So there are there. So these are the geometric lattices. Lattices that are non-geometric, and they have Whitney duals. Yes, the lattice of non-crossing partitions. So we show that there is a labeling that Stanley has defined before. It's also an EW labeling, and we have a Whitney dual for the poset of non-crossing partition, the lattice of non-crossing partition. But there are some other that even they are not lattices. So let me show you these two examples here. So these are posets that come from the theory of operats. So Bruno Valette related a property that is called causality of some families of operats to the Cohen-Macaulayness of maximal intervals of certain posets. So these are two posets associated to two operats. The first poset in the top, we call it, or people call it the poset of pointed partitions. It's similar to the poset of partitions, but you start in the bottom with pointed elements. And every time you start merging, so you merge two pointed elements, and then you decide who keeps the point. So for example, if I merge 1 and 2, either 1 keeps the point or 2 keeps the point. If I merge these two blocks here, 1, 2 with the 2 pointed and 3, then I can decide if 2 keeps the point, and I will be here in the middle, or if 3 keeps the point. This is called the poset of pointed partition. And then there is another poset very closely related to, it's called the poset of weighted partitions. Now they have a weight, and when I merge two blocks, I add the weights, and then I can decide to add one more. So for example, I add 1 and 2, they have weight 0, I can stay there, or I can add one more and get here. I merge these two blocks, and I get either here or here, okay? If you look kind of quickly to these two posets, they look kind of the same, but they are not. They are non-isomorphic. If you see, for example, in the middle, you have here an interval that has 4 covering relations, but here it has 6 cover relations. These two posets are non-isomorphic, but they have a very strange property. I forgot to mention that actually they are coming from the theory of operats. So in particular, the first poset was studied by Chapoton and Valette associated to operat perm of permutative algebras. And the second poset was defined by Dotsenko and Koroskin associated to operat com to the totally commutative algebras with 2 operations. So let's play the game of the Möbius numbers. So we compute the Möbius numbers for all of them, and then we add Whitney numbers of the first kind, so Möbius numbers by floor, and we also add the number of elements. And then this happens with these two posets. So actually, they are the same. So this again for Steven, like the question, the nonuniqueness, you can see it here. So we will call this phenomena like Whitney twins. So these two are not Whitney duals, but are Whitney twins. The Whitney numbers of the first kind and the second kind are exactly the same, even though these posets are clearly non-isomorphic. So we proved this with Michel Wax in 2014, that these two posets have the same Whitney numbers of the first kind and the second kind. Now in this recent project that we are soon going to post in the archive, we call these Whitney twins. So we have Whitney twins and Whitney duals. And now with Yeison, in his master's thesis, we actually computed, we found EW labeling and EW labeling for the poset of pointed partition. I want to point out that to find an EW labeling is not trivial. It's always like an artistic endeavor. It's difficult to find an EW labeling as it is to find an EL labeling. So he did a great job and find this EW labeling that will imply that this has a Whitney dual. And also, we also concluded that this is not an EL labeling, but it's a dual EL labeling. So he also has this property that help us to get homological conclusions. With Michel before, we have proven that this poset has an EL labeling, and this happens also to be an EW labeling. So both posets that are Whitney twins are Whitney dualizable. And this main theorem that we have this year, it says that actually these other two duals are also non-isomorphic. Okay, so think about these results a little bit as this important. The difficult question is like, if I give you two sequences of numbers, do you have a poset that this sequence has that this poset has the Whitney numbers of the first and second kind realized by these sequences? And also the other question is like, can even you flip it and still this be valid? This seems to be hard questions, but here what we are concluding is that both of these questions are, let's say, highly non-unique questions. So in particular, Whitney duals are not unique. Okay, so this is what I wanted to tell you today. Gracias.
Cool, great talk, Rafa. Let's give Rafa a round of applause. Awesome. So there was already an onslaught of questions and interest in the chat, and even a few in your talk. But are there any more questions for Rafa?
Mine didn't
Maria
get
has
answered
a
yet.
question.
Mine from the chat.
I'm sorry that I was doing a bad job with the chat. Yeah, can you repeat
Oh,
the question?
no. The
Yeah.
chat was excellent. I think Josh was answering so much. I was gonna ask, so I'll just read my question from the chat. Given two sequences, if you have a little WK and a big WK sequence, is there some like algorithm for constructing a poset with those Whitney numbers if it exists that like terminates if it doesn't exist?
Not that we know. We will love to hear this. Yeah, because this is exactly what we are thinking about. Like, it seems to be a very hard question because it's not one sequence. You can do something, but you need to be having the Whitney the Möbius numbers correctly also at every level. Yeah. So it seems
Right. I
to be
guess
hard.
the big W tells you where all the dots go, but then the little W you need to connect it to make those Möbius numbers. So it's that's interesting.
Exactly. And we show these sequences done are not possible to realize. Yeah. So what sequences are not Whitney realizable? And this work shows that actually there are sequences that are realizable but multiply realizable, because both the original posets were Whitney twins. So this is a multiplicity here. The duals are not isomorphic that are also Whitney twins, and they are dual of each other. There is even a third dual that I'm not mentioning here, but in our paper there is a third dual that is also Whitney dual to the original poset. So actually there are three duals that are non-isomorphic, and so there is a multiple of realizations here, a multiplicity of realizations. I should say, yes. Thanks, Maria. Yeah. So the question is, there is a question: does the lattice of non-crossing partitions admit a Whitney dual? And this is what I was mentioning before. Yes. So there is this labeling by Stanley in the classical paper on the lattice of non-crossing partition, and we show Josh and we show that this is an EW labeling. So we construct the Whitney dual of this, and the Whitney dual is always also. I want to mention this: the Whitney duals are always very nicely combinatorial. They are formed by combinatorial objects. Normally there are threes or fours. In the particular case that we have for the lattice of non-crossing partition is a poset on shredded paths. So you take the shredded paths and it can, you start with all the diagonals and you start kind of pushing some diagonals. And then a diagonal becomes some north, a diagonal, and an east step. And then you keep pushing. In the top, you will have all the Catalan paths, all the big paths. And this is the Whitney dual, or this is a Whitney dual of the poset on non-crossing partition. So it's very interesting from the point of view of combinatorics.
Maybe I can ask a question. Oh, unless did you have more to say?
There is another question by Steven here. Do you have any topological result about the order complex? So, Steven, so no topology. So I'm answering this question. Do you have any topological result about the order complex? So in principle, the EW labeling, it does not give a topological conclusion. If you, in addition, you have EL, like in this particular two cases that we have EL, we also have this topological conclusion that in particular implies that we have basis for the causal dual operads related to this perm and com2. But this is because these labelings that I show are either an EL labeling or also an dual EL labeling. But if you only have an EW labeling, there is no still any topological result. So it's open, let's say, to explore. Yeah, I'm sorry. Yeah.
No worries. Yeah, maybe I can sneak a question in. So I'm curious about applications. So it seems like passing from Whitney numbers of the first kind to the second kind, like, might simplify certain problems, because now I'm just looking at like elements in a poset at a certain rank. Do you have any examples of applications where you've been able to say something of interest that was maybe having to do with functions related to the Möbius function, sort of first kind perspective, and then you got out results easier using the Whitney dual?
Well, so I will say this. So in I didn't put this kind of question, but there is kind of an open question here, and this is we are exploring it currently with Jose Samper and Josh. So you could think about the.
Very nice talk. Okay, excellent. So now I think in our schedule, we have the planned critter showcase. So yesterday we had an activity where the idea was to get up off the couch out of the front of the camera for a minute and walk around and try and take a photo of a fun creature that you could find. So we actually had a few submissions, and I can now share these. Let me take a look at the things that people submitted. So there's not so many responses, but there's some pretty good ones. So, okay. Can everybody see my screen? Okay, cool. Let's start down here with Jessica's. So of course we have a dog looking very happy and loyal. So I'm personally excited to get a dog. All my friends are listening to me talk about getting a dog lately. So soon at a future AlCoVE, I will also be submitting a picture of a dog. More dogs, excellent. There's 2 in this one. That's adorable. And you managed to get them to look at the camera. I'm very impressed by that. Nice succulent plant. The easiest plant for a mathematician to take care of is a succulent, because you can just neglect the hell out of it and it will survive. So it will survive long droughts while you're busy thinking about a problem. There, I think, yep, there's a little bird in there. And then a motion shot. Excellent. Looks like a lovely day. Which campus is this? If you took the photo, are you online?
Yeah, it's an NC State. Right.
Nice. I thought it looked familiar. Cool. Looks like a lovely day. Oh, nice. And we have a bee nest. So I actually
Yeah, I didn't see any bee.
Oh, you didn't see any bees?
So I was safe.
Okay, cool. So actually, like down the street from our house, I had there's a parking lot that I walked through to get to the subway station, and there was like a sign that I didn't pay attention to for a while, and I was just walking through there, and then one day I looked at the sign and it said, "Here lives thousands of bees," and it's like actually a bee farm that I'd been walking through every day. So they never hurt me though. They're friendly. This is a beautiful photo. Look at these happy little caterpillars. Where was this taken, if you're in the chat?
This is my garden. We got some a lot of parsley seeded itself from last year, and now we have black swallowtails, apparently.
Wow,
Eating
that's
our
awesome.
yeah.
I mean, these are really, really beautiful caterpillars. And another dog, of course. I'm surprised that I haven't seen any cats. I guess where AlCoVE participants are tending towards dog people. And do grad students count? I don't know. We have to decide that as a community. Maybe it's a good icebreaker question for next year. For now, we'll say yes. Looks like they're having fun watching AlCoVE. That's what counts. Oliver, this must be the photo you were talking about yesterday. I'm not even sure what I'm looking at here, but I'm gonna go ahead and say this one wins. Where is the statue even? Nobody's in the chat to help us out here.
Sylvie just
maybe-
said in the chat.
Okay, cool. In Paris, excellent. Whenever I'm in Paris again, I'm